Hi everyone. Welcome to the afternoon session. It's my very great pleasure on behalf of the organizers of FPSA to welcome Professor Anton Mellit of the University of Vienna. Anton works in algebraic geometry and enumerative geometry, and he's uncovered fascinating connections to combinatorics, representation theory, and number theory. And I think he's best known in the algebraic combinatorics community, for his proof of the shuffle conjecture with Erik Carlsson. So welcome, Anton, and the floor is yours.
Thank you very much. Is the sound okay? Yes? Okay. So, unfortunately, I was really trying to come to India, but it didn't happen because of visa problems. So, let me start by introducing some interesting. So, the main interplay is here between some symmetrization and some enumeration. But so let me explain first what I mean by symmetrization. So so it is probably well known formula for the Schur function. So if lambda is a partition, then lambda variables xn can be written as follows. You put here the x1 to the lambda 1, x2 lambda 2, so on. Right? And then you divide by the product over I less than j, 1 minus, and then I have to do xj plus I. That's the right thing to do. And then I want to symmetrize this expression. So I will go over all permutations and I apply this permutation. So these are the Schur functions. And I want to advertise this, maybe a simple idea, which is well known, that to compute the Schur function, you can symmetrize variables one by one. So, for instance, suppose I already have from S number 2 and we obtain lambda. We need to do the following thing. So imagine, look at this as the corresponding formula for this as the lambda 2 epsilon lambda n. It sits here in the somehow. And you can imagine we already symmetrize with respect to those variables. Then what we need to do, we have to take, so let's call this f. We have to write f. We have to multiply it by x1 to the lambda 1. Then we have to put the part of the denominator which involves x1. So let's go. 1 minus j over x1. Okay, and then we have to symmetrize. But since we already have a function which is symmetric in n-1 variables, you don't have to go over all permutations here. For instance, you can go over all powers of the cycle. So the and the cycle. Then you need to go only over the powers of Cn. Okay. And that is the sum. Okay. And now you can think of a clever way to compute this sum. And here is the compute this. So we use a trick. Well, so let's call this operator the operator of symmetrization by R. So we denote this. By R of so you were not able to see the screen before, or how did it work? I just got the message now. Actually, everything fine. Can you hear me? Can someone say something?
Yes, it's good. We can see everything, Anton.
Okay, good. I haven't used this setup before, that's why I'm sorry. So you know this thing by R, some operation of f times x1 to -1. So the operation R involves dividing by the denominator and then symmetrizing. Then to compute this R, we have the following trick. So we want to compute R of some function, I don't know, g, x1, xn, which is symmetric in x2, xn only. Yeah. So what do you do? Since it's symmetric, so you write g as a function of x1 and the power sums p k, which is the sum of all variables. So you see, the trick here is I wrote everything as a sum of pk's, which is a sum of all variables. Initially, the function is given as a function of x1 and the rest of the variables, but I can still rewrite it in this way by changing variables. And then I can simply move out. So if I have some kind of R of x1 to some power a1, and then I don't know p1. So p1 and then p1 for pm. You can simply move out the p's because it's everything commute. So if you have some function which is already symmetric, we can clearly move it out of this symmetrization. So we can move out. And then I'm left with this function. So this now is simply the sum over all powers of Cn of x1 to the a over product of 1 minus xj over x1 And this you can compute. This is if you compute with the complete homogeneous symmetric function. So this is how you now you can what happens you to compute what you wanted to compute, to symmetrize. You reduce the problem to symmetrization one by one, right? And then to compute symmetrization in one variable, you have to express f in terms of the power sums of all the variables and a new variable x1. And then you move out the p. This you move out, you get here, and then you have to replace each power of x with c by the corresponding complete homogeneous symmetric function. So we have this. This motivates this spaces that VK that we introduced with Erik Carlsson for the proof of the shuffle conjecture is false. So one definition would be to consider that say that VK is a space of functions in variables x, y1, y2, yk, and then x1, x2, and then the sequence is infinite, and then we'll consider only those functions which are symmetric in the x variable. So this is, in other words, this is a space of functions which are symmetric in all but k variables. Indeed, in the previous construction, we wanted to work with functions which are symmetric in all but one variable. But you can also, if you think about the whole procedure, you start with a function which is not symmetric at all, namely for the Schur functions, we started with a function which is just a monomial, and then we kind of, if we do symmetrization one by one, we get the true function. So this will give you very well known raising operator formula for the Schur function. So in this, now if you have this space, what is the important things to, what is the important structure associated with this space? So what do we have? VK, what kind of interesting operations? Well, one operation is that as we saw in the previous page, we have the operation which we denote by d minus, and it goes from VK to VK minus 1. And this means this operation is symmetrized with respect to let's say yk. So, in other words, if you have f here, it depends on variables y1, yk, and then x1 and x2, and so on. And then it's already symmetric in x's, but now you want it to be also symmetric in the y. So symmetrize here. In one y, in the last one. Okay. That's one operation. And it sort of, you can think it decreases the number of variables, but it actually doesn't change the number of variables. It just makes it more symmetric. So if the function was symmetric in all but k variables, you get function symmetric in all but k minus 1. And then the second operation is another way. You want to be able to add some variables. And this operation is as follows. You have a function in this. Okay, and so on. And so on. And then you simply create a new variable. So you multiply it by one. So you simply see you are adding the variable in your variable, and then okay. So of course there are other things, like also we have some, we can permute by i's multiplied by one i's. So this is the kind of structure that we have. And it is a good idea to try to express different things, different operations. So perhaps we have a symmetric, we have a definition of some symmetric function, and using some symmetrization, then it's good to do symmetrization one step by step. And that's why these spaces we gave are useful. So, okay, is there any questions? Please don't hesitate. So, now, in fact, this was a bit of an oversimplification, because in fact, what we have with Erik is a new version of this. And this involves, so instead of writing some kind of sum over permutations, yeah, fine. We work with the Hecke algebra. Use Hecke algebra action. Polynomials by the difference operators. Few difference operators. You can look up the formula. So we have these operators T1, Tn minus 1, which correspond to simple reflections. And then we also have out of this we have other operators. So pi for any pi as n. And then it makes sense to write the sum over all permutations of these operators. And in this story, then, instead of true functions, we obtain, for instance, Hall-Littlewood polynomials. And the whole story is much gets more interesting a little bit. So yeah, that's one idea. now I want to start with another side. Now I want to explain again. If these are questions, interrupt. I want to start with the enumeration. So in algebraic combinatorics, we used to enumerate semi-standards. Well, as well. So we fix some shape. On this side, we will have a shape, which is a Young diagram or a difference of two Young diagrams. Yeah, so Young diagram will look like something like this. This is my lambda, and then you can look at something like this. So this is my shape, and then you fix another thing. So in this story, I will always have two pieces of data entering the picture. So one is the shape, another also you fix the content, which is the multi-set of integers. Positive integers. For instance, I can say if I take one, I take 3 times, and then I take 2, and then I take several 3, and so on. And this I denote by C. Multi-set of positive integers. And what I want to do, I'm considering fillings of the shape with this content. So I want to count, right? I want to interested in this number, which I can denote by S T of lambda C, which is the number of fillings. So filling is the bijection between C and lambda. You can say macro C to lambda, which is bijection, such that the numbers that you get in lambda are weakly increased in rows, increase in rows, and strictly increase in columns. So very classical thing to do. And then here is the first example of I want to advertise. Suppose you want to rediscover mathematics, and you were just playing with these numbers. So we have this S, Y, T, lambda, and C. We can vary lambda and we can vary C. Or we can even actually, I wanted to take not lambda, not straight shape, but a skew shape. So something more interesting. Yeah. So we are interested in counting this number and these numbers. So a good idea is would be to take the matrix where we kind of have all possible skew shapes and all possible content and make the matrix. So I don't know. So M and J equals S, Y, T, lambda I mu I, and Cj, where this goes over all shapes. And this goes over all possible multi-sets. But okay, first, when it is infinite, but you can restrict your attention to some. Of course, I mean, the numbers will be the same if you permute, if you kind of translate the integers that you're using. So let's say over. And then the good idea is to take the rank of this matrix. And it turns out that the rank of this matrix is much smaller than its size. So the size, if you can check that the size, for instance, the number of skew shapes is something like at least you can have exponential number of skew shapes of given size. But the number of turns out that the number of the rank is the number of partitions. So you can just plug this program in a computer, and then you can guess that the rank is always a number of partitions. So the partition function of n, which is much smaller. And so you should try to explain this phenomenon. Then you arrive at the beautiful theory that tells you that it turns out that so you discover that SYT C is a scalar product of a skew Schur function and a complete homogeneous function. So associated to the content. But this is a scalar product. These are all in the space of symmetric functions of degree and is the size of this, which is indeed the number. So this is how you could have guessed that you should get symmetric functions, because the rank is a number of partitions. You look at the sequence of these numbers, you recognize that there's a sequence of the partition function, and then you guess this statement. So something like that turns out works in other situations. And it's actually how we discovered this proof of the top integration. So it's another kind of more general kind of enumeration. So this is nicely explained in the paper by Shareshian and Wachs. As follows. So on this side, we still have shapes the same, but we use a different thing on the right side. Instead of C, we pick something called unit interval order. So what is a unit interval order? One way to say what is a unit interval order is to use a so-called Kettenberg function. So this is the same thing as the Kettenberg function. So this is a function it's just a sequence and tuple h1 to hn such that it is weakly increasing. Another condition is that every hi is less than equal than n and greater or equal than I. Okay, second. So this is the structure I want to use. You may ask me why is it a generalization of this content? And it is indeed, we can have some special cases of this Heckenberg function, which encode a multi-set of integers. But let me skip this detail. So for this Heckenberg function, we can also draw a picture. We have you draw equals here 1, 2 up to n, and you draw bar of size h1, h2, and so on up to hn. And then this is, you trace the boundary of this, you get a bit pass. So there is a bijection between Hessenberg functions and big pass. So why is it called the order? An order, let me explain why the order. So given, given this h, we say that if I is less than j, less than between 1 and n, we say that j is much greater than I if j is greater than hi. So this function kind of tells you that some numbers are really far apart than other numbers. Okay, so this tells you so the set from 1 to n now has two orders, which is like usual order, which is I less than j. And then this other order, which is the other order, so much greater than which I denote by this kind of curve. Okay. There are two orders. And now I will combine these two things and I'll explain what I want to enumerate. So what do we enumerate? So we enumerate bijections between the shape and set 1 to n, so that now before, so that if well, the numbers from 1 to n are sitting in the cells of the diagram, and then let's look at two adjacent numbers and introduce conditions. So first condition is one of the numbers on top of the number. Remember, for the Young diagrams, we had the rule is that the numbers must be strictly increasing in columns. So here we require that now they must be not just increasing, but increasing very fast. So the next number must be uh, much greater than B. So in other words, we can say that in columns, the numbers form chains. So chain is a sequence of elements of a partially ordered set, which so the first is less than the second, so. But in the on the other hand, if numbers are like this, one to the left to another, then we want to do the opposite thing. We want to relax the condition. And we relax it by saying that, well, before, how can you reformulate this condition that A is less or equal than B? A is less or equal than B means that A is not greater than B. So, but now we use this order. Yeah, so it means that A can be still greater or equal than B, or A and B are incomparable. Okay, so there is also this thing called incomparability graph, and that's how I'll explain the relationship. So we enumerate it by junction, so that yeah, and this we call p-tableaux. So let's denote the numbers by the number this by p. So what does it depend on? It depends on the shape, and it depends on the Heisenberg function. Now, I want actually not to do this. This was the older thing, but in fact, we count every p-tableau with Q weight, which is defined as follows. So Q to the number of I less than J, and I incomparable for this new order. So I is less than J, but not too much less than J, such that they are in the wrong order in our tableau. Such that I is to the right. Okay. Notice that numbers in each column are incomparable, so you never have such pairs of numbers in the same column. And this is when you, so this is basically, yeah, so you could play this game, and you could play the rank game. So for matrix again. So let's call this PQ H, and then the rank turns out to be is again the number of partitions, and that's how you should have discovered this theorem by Shareshian and Wachs. That if you the new H equals to again scalar product of this Schur function, and on the other side you have this I call chi, And this is so-called chromatic quasi-symmetric function. It's somehow called usually, it's actually a symmetric function. So, but for some reasons, it's always called chromatic quasi-symmetric function. Because it's not trivial, it's symmetric. Okay, so we have this chromatic quasi-symmetric function. And the story is continuous. So this is the, I think, very beautiful theorem. In particular, you can recover the definition of chromatic quasi-symmetric function by using the following kind of shapes. So if lambda minus mu is a union of columns, so it looks like this, then we are counting chains in our partially ordered set, because each column is just a chain and there is no restriction on the rows. And then as lambda mu is just a product of, so if this is A1, if this is A2, 3, it's just the product of the elements in the function. So you get the composition of this chromatic quasi-symmetric function in the forgotten base. So which is, so the convention is slightly different from the usual convention. That usually what I call chi h is just the involution applies to the usual chi h. The involution of symmetric functions which sends e to h. I hope this doesn't cause confusion. And then there is a beautiful, maybe most famous conjecture in the field is that Stanbridge and Q extended by Shareshian and Wachs. So original Stanbridge conjecture is about the enumeration of chains without any Q. And Shareshian and Wachs is the Q version. You say that chi is, in my notation, I have to apply omega, is h for the. So in other words, if you write the sum of some c lambda q h then c lambda is positive coefficients. And this conjecture is very open. Now I want to explain my contribution. This Erik Carlsson is the following discovery. So with Erik, we looked at the following thing. Suppose we take we break the D class into two. So in other words, what can we say? In other words, we choose k. K between n and 1, and we have then the function. We split h into two parts. We have first part up to hk. Let's see. So and then we can look at plus 1 minus 1 k. Okay. So if the graph of this h was like this, we kind of pick some point here, and then we partition everything into two parts. Here k and the other side k. Okay. But notice that the number here is over the diagonal. So these two things are what we call partial derivatives. And then we use a different matrix, the following matrix. Form a matrix where we so h prime and h double prime, we have there are two partial derivatives. And we glue them together. And then we take the corresponding chromatic symmetric function. So you connect these two. And so, for example, if you had some path this, and then you have another path like this, then you click this one and connect them together, and then you obtain this is the first part, and then the second part. Yeah. So cumulatively, you could say that you split you write your the set 1 to n as a union of two sets. And then you consider all possible unit interval over the sphere and unit interval over the sphere. And then so you have this matrix corresponding to all pairs of h prime and h double prime. And then we have computed the rank. We turn out the rank of that matrix is so much smaller than the number of partial paths. And then we were trying to guess what would be the space. What would be the space so that which kind of so we hope that the kind of the connected connection of the concatenation of the two paths is given by some operation applied to each part here. And then using dimensions, we could get that. So dimension turned out to be Well, I'm sorry, I will just get something. So we have something like sum of p n minus k and something like this, some kind of sum, and that will give us. So we get that there should be this. So this takes bk. So this is basically the number of dimension of degree 10 elements of the M. And M is here, the M is in the picture, so you have the distance of the point where you have H, right? And the leg end up hanging over the diagonal, the distance M. That has to be fixed for the game to make sense. So that's the okay, and then this, if you think about it, it gives the formula that, and then so chi h can be computed where you do the following: you start with 1, and you apply d plus or minus. And the following, so if you go up here, you push plus. But if you go down, it's minus. So you see that each d part naturally gives you a rule in, of combining d plus and d minus. You go left, you apply d plus. If you go down, apply d minus. So this is how we obtain the some explicit formula for the chromatic polysymmetric function using symmetrization operators. Now, so what I want to, I have 5 minutes now to talk about new developments of this. So when we were working with Erik Carlsson on this, we didn't even know that these functions are called chromatic polysymmetric functions, and we actually used some different version, which is some modification of that using platisms. But in the end, it turned out that it's not so difficult to see the connection. And the new development is the following. So now we want to try to understand. So in particular, with Erik, we didn't think about, we didn't know the theory of Shareshian and Wachs, and we didn't think about counting the p-tableaux. Now, but this point of view, this approach that I explained, it gives the following picture naturally. So p-tableaux counting. And we again write split the set of numbers that play into 2 subsets. And we, so this called A and this is B. And for each tableau, we can ask where is A, where the elements of A can sit. So imagine this is my tableau. And it is kind of clear that something like this is true, but not quite. So what is wrong? What is not true? Yeah, that in each row, sorry, in column, of course, all elements of A must be on top of elements of B. Is always on top. But in rows, it's not so. But in rows, we can have something like this, where the size of the row can get one bigger. But if this happens, then this must be this element must be in the subset of this last n elements. So this is this is translation of the, because to the left of this box must be element of B, and then the inequality that we have forces. And I'm just asking this question now. Now it seems that skew shapes is not the right thing to look at. It's not the right thing. Because this is what makes skew shapes natural in the classical theory was precisely this property that if you divide your elements into two subsets, you will have that A and B are always skew shapes. But in our case, it's not true. And so what is the right generalization of that? Then you have the right generalization is that if we have so we start with a partial weak path. So it looks like from here to here, and this distance is n, and this is m.
I'm so sorry, Anton. I think we're running out of time.
Yeah.
So.
Yeah. Okay. I was hoping that because I started later.
Yeah.
Now I will wrap it up.
If you can wrap it up in maybe 3 minutes or so.
Yeah.
Thank you.
So for this, we have we obtained this counting problem for a partial weak path, where we have the theorem, similar theorem that our chi h prime scalar product with certain function f, which depends on the skew shape, but now the skew shape can be more general. Is the number of q, like in my notation, corresponding p q of the shape and partial weak path. So once we prove this theorem, we now it is 2 minutes. We have this application to Loehr-Warrington conjecture. It's about certain problem like this is given in terms of Macdonald polynomials, And the shuffle conjecture is similarly, but certain Hall-Littlewood functions. And it turns out that these two are just enumerations of different kinds of shapes. Because in the shuffle conjecture, you can see that this is given by enumeration of some row of union of rows, and here you get this Loehr Warrington is about some shape. Say it like this. Basically, each row corresponds to a deep path, and here you have a deep enumeration of deep path, and here you have an enumeration of nested deep path, and so the two are equivalent. The two statements are equivalent. And since we proved the shuffle conjecture, it follows that the Warrington conjecture is true. And there is another independent proof by 5 authors that you can see on our pad. Okay, that's it. Thank you.
Yes, thank you very much for a fascinating talk, and thank you for sharing your secrets. Are there any questions? So I was going to ask where the nabla operator came in, but I think you answered it. Thank you.
Okay, yeah.
Thank the speaker again, perhaps.